Hello, and thank you for joining us for our Senior Design Showcase. My name is Ida Morris, and I'm the president of the 2021 CSUN Intelligent Ground Vehicle Team. We'll be joined by Julian Angelo Alcarantado and James Tavalugian to present the IGV Capstone project. To give a quick overview, we'll give some context for the competition goals and challenges. Then we'll discuss the design requirements and our solutions for the mechanical team, the electrical team, and the navigation and path planning team. This is the current breakdown of the team members on the IGV. The project easily supports interdisciplinary teams seen by the electrical engineering, and computer science teams taking part in a mechanical-based project. In total, we have 28 members. The competition is hosted in Michigan, and our team will be competing in the AutoNav Challenge. The purpose of this competition is to autonomously navigate an unmanned vehicle around the provided obstacle course. Reliability and safety are key portions of this event, so we must follow the course guidelines very strictly. Here is the 2021 course, but our design also takes into consideration previous maps and obstacles in order to stay relevant for future courses. This is a CAD representation of the IGV with all the sensors depicted. These components are playing a vital role in the operation of the IGV. I will now hand it off to Julian for the mechanical design.
Thank you, Eden. To begin, I would like to briefly introduce the design objectives of the mechanical team for the spring 2021 semester. We were to create and design a whole new frame to fully support any attached components onto the IGV safely. The chassis would still withstand and carry the entire load, whether stationary or in motion, and the mast was to be designed to be able to mount the cameras and the GPS antenna to the highest vantage point for the best field of view and the least interference for the signal. Moreover, with some research into other IGVs, modularity was found to be a key factor used by the top teams in the past few years, including CSUN's very own El Toro. So we applied that as the basis of our design and construction. Next slide, please. Here are the images of the mast and chassis designs the mechanical team has been working on. First, I'll be going over the mast. The mast is designed to be a rigid mounting structure to be placed on top of the chassis and to mount the cameras and GPS antenna. The chassis comes next. The box frame design is incorporated with straight vertical supporting members to increase the top surface area for a better fit for the laptop and 18-inch long payload. The bomb surface has been leveled as well to not only increase the area for mounting components, but to provide correct connection points to the suspension system. Next slide, please. And here is our suspension system. The suspension system as a whole is intended to be carried over from our predecessor's vehicle with some modifications to allow for application on our current design. Next slide, please. And here is an image of the IGV complete frame. Now I'd like to discuss the finite element analysis the mechanical team has conducted on the model. Here are images of the SAC studies done on the entire frame. Utilizing the weights of the components in our studies, the model appears to behave within expectation, which is to say the frame remains rigid. Next slide, please. And here are the results of the frequency study done on the entire frame. Unfortunately, we were unable to include the suspension system onto the simulation, and we were missing correct information about the spring constant of the frame. Thus, we treated it as a fixed point. With the suspension system, however, the expected frequency for mode 1 is to increase. Finally, I would like to talk about our cooling system. Next slide, please. We initially had planned to cool the battery pack, but with consultation from the electrical team, we deemed it unnecessary to do so. Therefore, we decided to cool the motor controllers, as those components produce the most heat during testing, and having those components be hotter than other components during runs would affect the overall performance of the IGV. Our design for the cooling system is shown in the image below. The casing is 3D printed, and a hole is on top to suck the air out, as CFD analysis has shown that pushing air out is more effective than pushing air in. I will now pass it on to James to talk about the electrical design.
Thanks, Julian. So what exactly is the electrical power team? Well, in short, the goal of the electrical team is to control and provide an adequate amount of power to the intelligent ground vehicle, as well as improve overall efficiency and lower manufacturing and maintenance costs. Next slide, please. So this semester, as far as battery pack design and assembly, the team used Energis Power Solutions 2x4 battery modules. Energis is a Lithuanian-based company who have a reputation of providing simple, lightweight, and high-density battery solutions to engineering teams and hobbyists all across the world. And what's nice about these modules is that because we would be connecting them with copper bus bars and standard fasteners, we could avoid soldering and spot welding, which is really important when you consider student safety in a project, and in particular, the overall design of a battery pack. And this semester, we try to create an even better battery pack than the previous IGVs while tackling on the task of putting it together by ourselves, which is something new to us and something that many other IGV teams haven't done. The idea for the team this past year was to mimic Tesla Motors' battery pack concept by using standard 18650 lithium-ion cells, which were chosen because of their high energy density and their relatively low cost. Next slide, please. One other thing that the team explored these past couple of semesters were computational fluid dynamic, or CFD studies, in order to justify the need of a cooling system for our battery pack. Initially, we ran through a few internal studies with a few different ideas, as shown on the left, that included a couple of different cooling cases, as well as a top-mounted cooling fan with a downward-facing manifold. After evaluating the state of the battery that was in the lab and conducting external studies that mimicked the opposing condition, which was no forced cooling for our system, we decided that a cooling system would be unnecessary for the needs of the IGV. Next slide. And so, because of the inherent inaccuracy of fluid dynamic simulations, we conducted 1D heat transfer calculations in order to further justify the results of our studies and justify why we eliminated the cooling system for our battery pack. These calculations examine the Reynolds and Nusselt numbers that pertain to fluid passing through heated tube banks, where the tube banks in our scenario would be each individual 18650 cell. And on average, compared to the exit temperature values calculated in the previous semester with active cooling, the system did increase about 3 to 5 degrees for about a 34.4 degrees C exit temp value. But again, this is nowhere near the 60 degrees C working temperature limit that was specified in the data sheets for the Energis battery packs. And hence why we decided to eliminate forced cooling from our system. Next slide, please. And after looking at the battery, we needed to find a battery management system to protect our custom battery pack while in use and while in charging. And during the semester, we looked at a few options and decided on the Texas Instruments BQ76PL455 EVM board. This system would allow for multiple boards to be paired in series to accommodate more cells if future IGV teams wanted to adjust anything, and it would still function in the same way as a single board. Next slide. Some other components that we needed to look at and decide on were our motor controllers and a high current clamp for our controllers. The motor controllers are used to interface with the logic and code from the system's computer to drive the motors, whereas the high current clamp protects the rest of the system from a backdriving voltage that could possibly damage from the system. These components were already on the existing IGV, and money could be saved since the team decided they didn't need to be replaced or upgraded this semester. Next slide, please. The electrical team also uses Cadence Allegro and EagleCAD to simulate and create the respective board for power distribution purposes for the IGV. And these simulations were used to obtain the desired output voltage and output current to the system before selecting an appropriate vendor to manufacture the board itself. Next slide. And at last, in an effort to simplify and streamline connecting the IGV's components to their respective power sources, we constructed a diagram on SolidWorks that provides an overview of the different components of the system, what type of connection each component has, and where it connects to. Our goal was to create a template to simplify the wiring of the IGV to the point where someone unfamiliar with the system could understand how to properly connect everything. And next is Eden with the IGV's navigation and path planning.
Thank you, James. Our all-encompassing design goal was to design a reliable autonomous system that will stay relevant for multiple years to come. This specific map incorporated barrels, GPS goal points, white lanes, and flags. We have also accounted for ramps, gates, and more since they have shown up in the previous year's maps. All the obstacles cannot be handled by a single vision system, so we're incorporating multiple sensing methods to accomplish our goal. To deal with the spray-painted lines, we're using an RGB camera with 2D image processing. For the ramps and flags, we're using object detection. And finally, for the taller obstacles, we're using a 2D LiDAR sensor for SLAM navigation with GPS integration. To handle all these simultaneously running systems, we're using the robot operating system for operation and development. ROS allows us to connect independent programs and utilize lots of open source software. Here's our system architecture from sensor input to data processing to motor control. The following navigation methods all publish velocity commands independently, so we use a velocity multiplexer to prioritize the incoming commands for the motors. SLAM is a method of simultaneously locating the robot and mapping the environment. This solution pulls data from the inertial measurement unit, the 2D LiDAR, and the GPS sensors. These sensors come together to create a map for the path planning algorithm to use for navigation. On the right, we have a SLAM system running with no form of autonomous navigation or path planning, just for this depiction. ROS allows us to convert GPS coordinates to local navigation goals for the IGV to move towards. For the lane following problem, we are using our wide lens cameras to see these lanes. This video feed then goes through an image processing program to find the correct motor controls needed to follow these lanes. In summary, we blur the initial image, convert it to grayscale, and isolate the brightest pixels since we are isolating the white lanes. We can then create virtual lines using OpenCV's hue transform to give us our final motor control. To end our navigation algorithm, we are using object detection to find certain objects in the video feed and create motor control outputs based off those images. These objects would be depicted incorrectly or not depicted in vision or purely SLAM. In this frame, we have created a custom object detection model that specifically detects cones. We can then use these located cones to create virtual lines using a polyfit and center the robot between those slopes. Thank you for your time. Are there any questions?
Let's see. Hey, yeah, I have a couple of questions.
Of course.
I don't know if I missed it, but is there any mass or weight criteria?
For the competition?
Yeah, that's right.
So we can explain the weight with the better image. So the robot is, there's no weight criteria, but we did try and reduce the weight from previous years. We also tried to reduce the center of gravity from previous renditions of the IGV, and I think this robot is around 200 pounds.
Specifically, the robot is 190 pounds. It's a weight reduction of 20 pounds from our previous iteration.
Cool, but there's no competition-driven criteria.
No.
And then just a question about the cooling design. Is there an over temp condition, or maybe what ambient conditions did you assume in the analyses?
We had assumed room temperature, just standard.
Well, so it was a little bit problematic because we had been using another simulation, ANSYS, to get the temperature values for the battery cells. And then what we did was use SOLIDWORKS flow simulation and specify that 41 degrees C to each individual battery cell, and then an ambient temperature of 26 degrees C. And then we played around with the different velocities and external and internal studies. But admittedly, it was a bit difficult because there was no formal class on flow simulation that I had taken, and ANSYS was very difficult, and people had said that flow simulator was the best option for students like us.
Did you think about doing any hardware testing with some thermocouples and fans and see what temperatures you're seeing?
Well, actually, truthfully, a lot of the semester was spent doing these simulations and design because of the whole COVID situation.
Mm-hmm.
And personally, I didn't get to go into the lab, so.
Cool.
Do you mind showing the first page where you show the design spec and what the payload? I think you had a payload of 20 pounds. Is that right?
Yes. I think I passed it here.
There it is. And the course itself is given to you, right? You know beforehand what path you're going to follow. You were talking through that, I think.
Yeah, yes, we're given an example of the course, but we're not giving any sort of preliminary. The only information we're given previously to like starting a run is the GPS coordinate waypoints that we have to travel towards and hit each one in a sequential fashion.
Is there some kind of sensing, or do pause there or something?
We kind of implemented the GPS into our SLAM navigation. So ROS allows us to use something called a specific node called GPS goal, which will translate your your current GPS position, your goal position that you publish to it, and then convert that into a local path.
Got it. Got it. That's great.
There's a quick question from Professor Bishay. He's just wants you guys to clarify. Did you start in spring 2021 or fall 2020?
So we actually started spring 2020, and then that team lasted until fall 2021 in December, and then they handed off to our team, which has progressed, and we built this robot for the 2022 competition, and we'll do the physical manufacturing for that competition.
Thank you. So we are pretty much on time, which is amazing. So I'd like to thank the Intelligent Ground Vehicle team for the presentation and everybody for their questions.